I'm here to describe to you a patent. My name is Steve Arnold. I'm from the Micro-Particle Photophysics Laboratory. This patent is about discovery made by Sika Shapova and described by myself from my laboratory at then the Polytechnic Institute of New York, now known as the NYU-Tandon School of Engineering. The document originated as a provisional application in August of 2010, long before any publications were associated with this phenomenon. So what is the phenomenon? Well, I haven't described this before in YouTube's, but basically it's the following. When a nanoparticle comes to the surface of a microcavity, it shifts the frequency of the microcavity. If that nanoparticle is a single protein molecule, then the shift is incredibly small, well below the noise in at least our experiments. So if you want to see this sort of thing in real time, it turns out a plasmonic particle on the surface reveals the protein and enables you to measure properties of it. So here it's shown as this object on the surface. I like to call it a plasmonic epitope. It's a particle that sticks out from the surface of the microcavity, here shown as a spherical microcavity. And here is this diagram showing this nanoparticle coming to a gold nanoparticle. First, I'd like to say that the patent is loaded with data which proves the effect. This data taken in 2010. The actual cause of the effect for an external cavity of this nature, an open cavity, is described by the reactive sensing principle, which basically says that when a dielectric particle comes to the evanescent field of a whispering gallery mode, it shifts the frequency of the whispering gallery mode. This is the way this was interpreted. It's just that the field at the surface of the plasmonic particle, which is near resonance with the whispering gallery mode, is much greater than for the naked cavity itself. As to the plasmonic particles, as you can see here in this sort of yellowed area, they can be nanoshell, nanorod, non-concentric sphere, nanodot, or contain dimers or several plasmonic particles placed in close proximity. The idea here is that clusters can often change the properties of the microcavity resonance, reduce the scattering of a cluster compared to a single plasmonic particle. So it covers just about every possible epitope. I'll just page down here, hopefully get quickly, and I'm sorry for the delay, to the next point. The next point is that it talks about the assembly of this thing by light forces, although that's not the only way this can be done. But more importantly, it talks about the kinds of microcavities that can be involved here. Microcylinders, microcapillaries, microbubbles, microdiscs, microrings, micro-racetrack, micro-bottle resonator, micro-toroids, and other resonator geometries that can support a whispering gallery mode with plasmonic particles. also it says that it's simply a particle within the modal volume of the microresonator. It is to Sika-Supova's credit that she managed to get all of these things in here and imagined all of them. Well, claims are where the heart of a patent is. The method here is basically place something on the surface, an epitope, which is plasmonic, or several of these things that are plasmonic, and enhance signals, namely frequency shift signals. She also talks about changing the splittings which can occur in the process. Well, let me just go through one or two of these things because it really is very thoroughly written. The method of claim 1, that's that first thing I talked about, within the dielectric microresonator has a geometry selected from microsphere, microring, microcapillary, microcylinder, microracetrack, microdisc, micro-toroid, microbottle, microbubble. The method within the dielectric microresonator is made of a material. She's covered a tremendous number of materials: silica, glass, silicon nitride, silicon oxynitride, gallium nitride, gallium arsenide, and indium arsenide. The plasmonic epitope, as I like to call it, can be a nanoshell, a nanorod, a non-concentric sphere, and a nanodot. Now remember, when there are claims, it means that these have already been vetted by the examiner, and these were what was allowed. The method of claim 1, wherein the plasmonic nanoparticles consist of dimers or several plasmonic particles placed in close proximity as a cluster. And I talked about this just before. Create a cluster for the purpose of reducing scattering so that you can basically preserve the line width and therefore the sensitivity. There are in all 37 claims that were allowed by the Patent Bureau. And I think the best way for anyone to go through this who's interested in microcavities and the state of the art of these things is basically to read the patent. So what I've done is, in my first comment on this YouTube, I will place a copy of this patent that I'm reading from. I thank you for your attention, and I'll see you again in further YouTubes. Bye-bye.